Hey everyone, welcome back. Quick question for you. When you open Instagram and it instantly shows you photos from your friends, ads tailored to stuff you searched last week, and your own profile info, how does it do all that instantly without melting down? The answer is databases. And today, we're going to crack open exactly how they work. From the basic building blocks all the way up to the language that powers almost every app on your phone. By the end of this video, you'll understand why databases replaced old-school filing systems, how data gets organized into neat tables, what SQL actually does, and even how companies use your data in ways you probably never thought about. Let's get into it. So here's the roadmap for today. First, we're going to talk about why databases exist at all, what problem they solve compared to old flat file systems. Then we'll dive into the big one, the relational model. That's the table-based system almost everything uses today, including how to design tables properly so you don't end up with a mess. After that, we'll touch on object-oriented databases, a different way of thinking about storing data. Then we'll talk about how databases protect themselves from chaos, things like crashes and multiple people editing data at once. We'll also look at traditional file structures, the OG methods like sequential files, indexes, and hashing, which still show up under the hood of modern systems. Then a fun detour into data mining, finding hidden patterns in mountains of data. And finally, we'll wrap up with the social side. What does all this mean for your privacy? Lots to cover, so let's jump in. Okay, picture this. It's the 1960s. A company has a payroll department, a personnel department, an inventory department, and a sales department. Each one keeps its own separate file of information. Sounds fine, right? Except, what happens when an employee changes their address? Now, someone has to go update that information in like 4 different places. Miss one, and now your records don't match. This is the flat file problem. A flat file is basically a one-dimensional list. Think of an old-school spreadsheet that only shows information from one angle. If you have a flat file of music albums organized by artist, but you want to find all the albums of a certain genre, you're stuck. The file just isn't built to answer that question easily. A database, on the other hand, is multidimensional. It links information together so you can look at it from lots of different angles. Same data, but now 5 departments can all pull from one shared integrated pool of information. Change an address once, and everyone sees the update. Now, here's something important. Just because everyone can access the database doesn't mean everyone should see everything. That's where schemas and sub-schemas come in. Think of a schema like the blueprint for the entire building. It describes the whole database structure. A sub-schema is like your key card. It only gives you access to the rooms you're allowed into. So, a university registrar might be able to see which professor advises which student, but not that professor's salary or employment history. Meanwhile, the payroll department sees the salary info, but has zero idea about advising relationships. Same database, different views. That's the power of subschemas. And how does all this actually get executed? That's the job of the DBMS, the Database Management System. Think of the DBMS as a translator that sits between the application, the actual app you're using, and the messy, real storage on the hard drive. The app says, "Give me this person's info," and the DBMS goes and actually fetches it, without the app needing to know how or where the data is physically stored. This separation is huge. It's called data independence, and it means you can completely reorganize how data is stored on the back end without breaking the apps that use it. All right? This is the heart of the whole video, so buckle up. The relational model organizes data into relations, which is just a fancy word for tables. Picture a spreadsheet, rows and columns. In database terms, a row is called a tuple, pronounced tuple. Yes, people argue about this. A column is called an attribute. So if you have a table of employees, each row is one employee's full record, and each column, name, address, ID number, is an attribute describing that employee. Simple enough, right? But here's where it gets interesting, and where a lot of beginners trip up. How do you design these tables properly? The problem with cramming. Everything into one table. Let's say you start with a table of employees. ID, name, address, social security number. Easy. Now your boss says, "Hey, can we also track job history? Like what jobs each person has held, when they started, when they ended, what skills are required, which department?" Your first instinct might be, just add more columns to the same table. Job title, skill code, department, start date, end date. Tack 'em all on. Sounds reasonable. But here's the problem. Now, instead of one row per employee, you have one row per job assignment. If someone has held 3 jobs over the years, their name, address, and SSN get repeated 3 times. That's wasteful, but it's also dangerous. Here's the scary part. Imagine one employee, let's call him Sam, is literally the only person who's ever held a particular job. Say, department head, job code A1. If Sam leaves the company and you delete his row, you just accidentally deleted the entire record of that job existing. The information that job A1 even exists and what skill level it requires vanishes along with Joe's personal info. That's called a deletion anomaly, and it's a classic sign that your database design needs work. The fix: split it into multiple tables. The solution? Break things apart based on what they're really about. In our example, we actually have 3 different concepts tangled together. Information about employees, name, address, SSN. Information about jobs, job title, skill code, department. Information about assignments. The relationship between an employee and a job start date, end date. So we create 3 separate tables: an employee table, a job table, and an assignment table. Now, Joe's personal info lives in one place. The job D7's info lives in another place, completely safe even if Joe leaves. And the assignment table just links the 2 together with start and end dates. This is called designing for a lossless decomposition, splitting a big table into smaller ones without losing any information. And it's not automatic. Sometimes splitting a table the wrong way actually loses information. For example, if you split a table with columns employee ID, job title, department into 2 separate tables, one with employee ID, job title, and another with job title, department, you might think you preserved everything. But now, if multiple departments have a floor manager position, you can no longer figure out which department a specific employee's floor manager job is in. The connection got lost. That's a lossy decomposition. Bad news. The takeaway: relational database design is genuinely an art. You need to think carefully about what each table represents as a single concept. Ever wonder what your apps are actually doing every time you tap a button? Whether it's posting a photo, editing your profile, or deleting an old message, under the hood, it all boils down to just 4 operations. We call them CRUD: create, read, update, delete. Let's break it down. Create is adding something new. Sign up for an app, and boom, a new row gets created in a database somewhere with your username and email. New customer, new product, new post, all creates. Retrieve, sometimes called read, is just fetching information that's already there. Scrolling your feed? Searching for a product? The app is asking the database, "Hey, give me this data," and the database hands it over. Update means changing something that already exists. Moved to a new city and updated your address? Changed your profile picture? Same record, just new information inside it. And delete? Well, that one's pretty self-explanatory. Removing a record entirely. Deleting an old post, canceling an account, clearing out an item from your cart. Here's the thing. Literally every interaction you have with an app maps back to one of these four. And once you start noticing it, you can't stop seeing it. Next time you use an app, try guessing. Is this a create, a retrieve, an update, or a delete? That's CRUD, the four moves that run the entire digital world. Now, here's the thing. In practice, nobody writes out three separate create, retrieve, update, and delete steps every time they want info. Instead, we use SQL, Structured Query Language. SQL is the actual language that most relational databases speak, including MySQL, which powers a massive chunk of the internet. An SQL query has basically three parts. Select. Which columns attributes do you want? Confusingly, this maps to the project operation we just talked about. From which tables are you pulling from? This is where the join happens, if you list multiple tables. Where? What condition do the rows need to meet? This is the select operation from before. So a query like that in the blue box is basically saying, join the assignment and job tables together wherever their job IDs match. Then filter down to only currently active assignments where the termination date is just an asterisk, meaning still employed, and give me back just the employee ID and department for each. It looks like a list of instructions, but really, you should read SQL as a description of what you want, not a step-by-step recipe. You're telling the database, here's the shape of the answer I need, and the DBMS figures out the most efficient way to actually get it. SQL also handles changes to the data, not just questions. Three big ones. Insert into. Adds a new row, like hiring a new employee. Delete from. Removes a row like an employee leaving. Update. Modifies existing data like changing someone's address. These four, select, insert, delete, update, cover basically everything you'd ever want to do with a database. In our employee example, you'd have an employee object, a job object, and an assignment object, all connected by lines representing their relationships. Follow the links from an employee object, and you find all their assignments. Follow the links from those, and you find the jobs they're connected to. What's the big advantage here? Objects can be intelligent. A relational table just stores raw data. It doesn't do anything. But an object can contain methods, little built-in programs. So an employee object could have a method that says, report my job history, and it would automatically know how to gather that info from its linked assignment objects without some external program having to manually search through tables. Another advantage, flexibility with weird data types. Say you want to store an employee's name in a way that handles first names, middle names, surnames, nicknames, all the messy variations. In a relational table, this gets awkward because you'd need a rigid, fixed set of columns. But in an object-oriented system, you can hide all that complexity inside the object itself. The object can intelligently report, just give me the surname, or give me the full name depending on what's asked, and all the messy logic is encapsulated inside. One more concept worth knowing, persistence. Normally, when a program runs and creates objects, Those objects vanish, poof, when the program ends. That's called being transient. But database objects need to stick around after the program closes. Objects that are saved permanently are called persistent objects. And making that happen is actually a big design challenge for object-oriented database systems. Here's a scenario. You're transferring $100 from your checking account to your savings account. Behind the scenes, that's actually 2 steps. Subtract $100 from checking, then add $100 to savings. What happens if the power goes out between those 2 steps? Poof! $100 just vanished from existence. This is why databases use something called the commit/rollback protocol. Every transaction steps get written to a log, basically a permanent diary of everything that's about to happen, before it actually happens. The moment all the steps for a transaction are safely recorded in the log, that's called the commit point. Once you hit the commit point, the database is committed, guaranteed that this transaction will happen no matter what, even if the system crashes right after. But if a crash happens before the commit point, the database uses the log to roll back, basically undo whatever partial steps were completed, like hitting undo on a half-finished edit. Now here's a trickier problem. What if 2 transactions are happening at the same time on the same piece of data? Imagine your account has $400 and somehow 2 separate withdrawal requests. One for $100, one for $200. Both read the balance as $400 at almost the same moment. Each one calculates the new balance based on that original $400, and then both write their results. Depending on the timing, you could end up with the wrong final balance. This is called the lost update problem. The fix is locking. When a transaction needs to use a piece of data, it can request either a shared lock, meaning I'm just looking, others can look too, or an exclusive lock, meaning I'm about to change this, nobody else touches it. It's like a library book. Multiple people can read a reference copy, but if someone's actively editing the master copy, everyone else has to wait. Of course, this creates a new problem. What if transaction A is waiting for a lock held by transaction B, while transaction B is simultaneously waiting for a lock held by transaction A? Neither can move. That's deadlock. And it's like 2 cars facing each other on a 1-lane bridge, neither willing to back up. One elegant solution is the wound weight protocol. Older transactions get priority. If an older transaction needs something a younger transaction is holding, the younger one gets forcibly rolled back and has to start over. Over time, every transaction eventually ages enough to get priority, so nothing waits forever. Before all this fancy database stuff, computers stored data in simpler structures. These ideas are still used under the hood of modern databases, so they're worth knowing. A sequential file is exactly what it sounds like. Data stored in one long line, read from beginning to end. Think of an old cassette tape. To get to song 7, you have to physically pass through songs 1 through 6. To find the end, programs look for a special marker called a sentinel, or rely on the operating system knowing exactly where the file stops. That's the end of file, or EOF. Sequential files are great when you process everything in order, like running payroll for every employee, one after another. But they're terrible if you need to jump straight to one specific record in the middle of a huge file. Imagine trying to find one specific contact in a phone book. But the phone book isn't alphabetized, and you have to read every single entry from the start. Painful, right? That's where indexed files come in. An index is like the index at the back of a textbook. Instead of scanning the whole book to find photosynthesis, you check the index, see it's on page 247, and jump straight there. A file's index stores a list of key values, like employee ID numbers, along with the location of each corresponding record. Indexes are often loaded into main memory first, so lookups are lightning fast. And then there's hashing. Honestly, one of the coolest ideas in this whole topic. Instead of looking something up in an index, hashing calculates where something is stored, directly from its key. Here's how it works. You divide your storage space into a bunch of buckets. Then you take a record's key, say, an employee ID, run it through a hash function, often something as simple as divide by the number of buckets and take the remainder. And that remainder tells you exactly which bucket to put the record in. So if you have 41 buckets and an employee's ID number, when converted to a number, divided by 41, gives a remainder of 3. Boom. That record goes straight into bucket 3. No searching needed. Want to retrieve it later? Run the same calculation again, and you know exactly where to look. Why 41 and not a round number like 40? Because 40 has lots of factors. 2, 4, 5, 8, 10, 20. If a bunch of your employee IDs happen to be multiples of 5, they'd all pile into the same handful of buckets, creating lopsided clusters. Using a prime number like 41 avoids this. It spreads things out more evenly. Clever, right? But even with a perfect hash function, collisions are basically inevitable. 2 different keys landing in the same bucket. In fact, math shows that even with a well-designed hash and only 8 records placed into 41 buckets, there's already a better-than-even chance a collision has occurred. Designers handle this by letting buckets grow, or by using overflow areas. The general rule of thumb: keep your load factor, the ratio of stored records to total capacity, under 50%, and definitely don't let it creep past 75%, or performance starts to degrade fast. Okay, shifting gears. Data mining isn't about retrieving known facts from a database. It's about discovering patterns you didn't even know existed. It's done on data warehouses, basically big snapshots of data that don't change while you're analyzing them, because finding patterns in a moving target is way harder than in something frozen in place. There are several flavors of data mining. Class description, finding common traits within a group, like, what do people who buy compact cars have in common? Class discrimination, finding what makes 2 groups different, like, what separates people shopping for used cars versus new cars? Cluster analysis, discovering natural groupings you didn't define ahead of time. Maybe you analyze the ages of people who watched a kids' movie and discover there are actually 2 distinct age clusters: little kids and their parents. Association analysis, finding links between things. The classic example: people who buy chips also tend to buy beer and soda. Outlier analysis, finding the weirdos, the data points that don't fit the pattern. This is huge for catching credit card fraud. If your spending suddenly looks totally different from your normal pattern, that's a red flag. Sequential pattern analysis, finding trends over time, like in stock markets or climate data. And one fun-related field, bioinformatics, using these same pattern-finding techniques on DNA and proteins. Computer science literally helping decode biology. Step 1. We have an employee table. Each row: employee ID, name, address, SSN. Simple, clean. 1 row per person. Step 2. We have a job table. Each row: job ID, job title, skill code, department. This describes the jobs that exist in the company, independent of who's doing them. Step 3. we have an assignment table that connects the two. Each row: employee ID, job ID, start date, term date with an asterisk meaning still in this role. Now let's ask a real question. What department does employee 23569 currently work in? Here's the play-by-play. Look in assignment for rows where employee ID equals 23569 and term date equals asterisk, meaning currently active. That gives you a job ID. Join that with the job table, matching on job ID. Project, just the department column. In SQL, this whole multi-step dance becomes one query, as shown in the highlighted box. See how elegant that is? You're describing the answer you want, and the database figures out the join, the filtering, and the column selection all in one shot. Now let's look at the hashing example again. Visually, imagine 41 numbered storage buckets, 0 through 40. Employee ID 23569 gets converted into a giant number. Computers see everything as numbers under the hood. That ID is really just encoded characters. Divide that giant number by 41 and say the remainder is 3. That record goes into bucket 3. Done. No searching, no index lookup. Pure math gets you there. But here's the catch. What if employee IDs 14, 55, and 96 all happen to produce a remainder of 14 when divided by 41? They'd all pile into bucket 14. Now, retrieving any one of them means searching through all three. That's clustering in action, and it's exactly why hash function design matters so much. One more practical example. Merging files. Imagine you have two sequential files of customer records, each sorted alphabetically by last name. File A has records B, D. File B has records A, C, E, F. You want to combine them into one sorted file. The merge algorithm does this by comparing the next record in each file, picking whichever comes first alphabetically, writing it to the output, and advancing that file's pointer. Repeat until both files are empty. It's basically how two people merging two sorted decks of cards would do it. Always take the smaller card from whichever pile has it on top. This merge process is also the secret behind merge sort, one of the most famous sorting algorithms in computer science, built on exactly this same idea. Databases beat flat files because they let you view the same data from multiple angles. And schemas/subschemas let different users see only what they're allowed to see, while a DBMS handles the actual heavy lifting behind the scenes. The relational model organizes data into tables relations, made of rows, tuples, and columns attributes. Good design means splitting data into multiple tables based on what they actually represent, avoiding redundancy and dangerous deletion anomalies, while making sure your splits don't accidentally lose information, lossless decomposition. Select, project, and join are the three fundamental moves for getting data out of relational tables. And SQL is the language that wraps all three into clean, readable queries. Object-oriented databases offer an alternative, linked, intelligent objects with built-in methods, which shine for complex or multimedia data, and which need to be made persistent to survive after a program ends. Transactions need protection. The commit/rollback protocol uses logs to recover from crashes, while locking shared versus exclusive prevents chaos when multiple transactions touch the same data, though it can introduce deadlock, solvable with protocols like wound weight. Traditional file structures, sequential, indexed, and hash files, are the building blocks underneath modern databases, each with trade-offs between speed, order, and direct access lookup. Data mining finds hidden patterns, clusters, associations, outliers, trends, in static data warehouses, turning raw data into insight, and yes, raising real ethical questions about privacy along the way. And speaking of privacy, every time you give your info to a store, a website, or an app, you're feeding a database that can be linked, cross-referenced, and analyzed in ways that go way beyond what you originally agreed to. Worth thinking about. That's the whirlwind tour of database systems. If this helped things click for you, smash that like button, subscribe for more computer science breakdowns, and drop a comment if there's a topic you want me to tackle next. Thanks for watching, and I'll see you in the next one.